Hello, everyone. Welcome to the last lecture of the semester. We're moving on to chapter 13, section 13.3, finite state machine with no output. So this is FSM. All right. So here are a few homework problems you can try for this section. All right. So yeah, so this is an example of a finite state machine, FSM. Well, think of this. This is a vending machine that you see around campus, right? Or even like the snack machine, where you input some money and then they give you a bag of chips or something. But then you can see that it doesn't take like 25 cents only. It take like 5 cents, 10 cents, and then penny if sometimes they have it too. Then depend on how many coin you insert in, or what's the price of the item you want to have. Then they just give you the item and give you some change on that. So here is the example, right? Suppose that you starting the procedure, and let's say you want to insert 25 cents. If the cost is 25 cents, or the cost is 30 cents, right? So you can input 25 cents. So if you input 25 cents, it takes you directly to step 5. And then you put 5 more cents, it takes you to step 6, and that's when they eject the item out, right? So that's the idea. Or you can input 5 cents at a time, right? You can put 5 cents at a time. It still take you to the final state where they eject the price, right? So or orange juice, apple juice, things like that, depend on what they have. You can see here the description, right? Orange juice and apple juice take like 30 cents each, thing on that. So when they have enough 30 cents, they will reproduce the orange juice and apple juice, things like that. But then you can see that sometimes you take 10 cents, you can take 10 cents at a time, and then after that you can skip a bunch of the step, and then you put 5 cents in the last. So that's the idea, right? Sometimes you take 10 cent and then 5 cent, or you can take 5 cent and 25 cent. It still take you to the final state. So this is what we call finite state machine learning. All right, so that's the concept of the idea to have today. So before we go to that FSA, so we'll take a look at a few definitions. So first one is set of strings. So the FSM, finite state machines, SFM would be the shortcut for that, with no outputs, but some states designated as acceptance state. Okay, so that's the acceptance state. That's pretty much the final state that we have, so that we can recognize in our languages. The concatenations of A and B, where A and B are subsets of V star. V is a vocabulary denoted by AB. It contains the set of all strings of the form XY, where X is a string in A and Y is a string in B. All right, so kind of distributed property start with the set A to everything in set B and vice versa, and then so on. All right, so the set of A0 will be just lambda. So here is the example. Suppose we have the set A contain 2 bit string 0 and 1 1, and the set B contain bit string of 1 1 0 and 1 1 0. Then the concatenations of A and B, or AB, will be 0 1 0 1 0. So technically you can imagine that, okay, I'm going to take this 0 here and I map to the 1 here. And then I'm going to take the 0, map to the 1 0. I'm going to take the 0 and map to the 1 1 0. So that's what you see in the first 3 items. And then once you're done with that, you go back to the bit string 1 1 and you map it again. and then you mapped it again, and then you mapped it again. So that's how you see the last 3 string. Yes, yeah. So that's what we call the concatenation of A and B. All right, sounds good. Yeah. Okay. So yeah, think of a distributed property of a bit string from one set to another set. All right. So on the other hand, when you do BA, you do the opposite. All right. So you don't go from A to B, but you go the reverse order. You want to go from B to A. All right. So again, before you go 0 to 1, and then you're gonna go take the 1 and go to 0, and then 1 go to the 1. Once you're done with that, you're moving on to the 1, 0, 0, and then 1, 1, 1, 0, and so on. So you can see here 1, 0, and then 1, 1, 1, and then 1, 0, 0. So the element of B have to go first, okay? And then 1, 0, 1, 1, and then 1, 1, 0, 0, and then 1, 1, 0, 1, 1, right? So that's the idea of that. Okay, sounds good. Another one that we have is the clinic closure. If A is a subset of V star, the clinic closure of A denoted by A star is the set consisting of arbitrary long strings of elements of A. So technically, A star will contain the unions of all element of A start from 0 to infinity. So depend on what they have, right? So we, you know, A to the K. All right, so here's the example. Suppose we have the 3 set A, B, and C. A contain the 0-bit string, B contain the set 0 and 1. So that's 0 binary, right? 0, 1, 0, 1. And C contain only 1-bit string of A1, 1, right? So different between B is that you have 0 and 1. So that's just repeated 0 and 1. So the clinic closure of A will be, you know, 0 and then 2, 0, and then 0, 0, 0, 3, 0, things like that. Therefore, the clinics of A will be 0 to the n, where n equal to 0, 1, 2, 3, to the all the way to infinity. All right, and then B star will equal to V star. It's a vocabulary, the bit string 0 and 1. All right, so it's just the whole space that we would have. And you can see that the group C contain the bit string of 1, 1 together in one strike. So we have C star will equal to 1 to the power 2n, because you know you can see because n number 1 repeated 2 times, so 1, 1. That's what it is. And the I would be just 1, 0 repeated itself. So we're gonna have to go like 1, 1, 1 as, you know, double 1 at the time for that to happen. So that's the idea of clinic closure of A. All right, so let's get to another example here. See, we can, you know, find A, B, B, A squared, and then B to the third. So you can see here, AB is quite straightforward. We, you know, AB, we take that and distribute over there. So again, A will be first, A 0, 0, and then 0, 0, 1. Okay. All right, and the next one is 1, 1, 0, 0, and then 1, 1, 0, 1. So that's AB. Now BA, you start with the B first, so you want to go 0 and then 0, right? B first, and then 0, 0, 1, 1, and then 0, 1, 0, and then 0, 1, 1, 1. That's BA. Now how about A square? Well, A square is the same thing as AA, right? So again, A equal to 0, 1, 1, and then A equal to 0, 1, 1 again. So you just kind of map by itself. So you're gonna have 0, 0, 0, 1, 1, and then 1, 1, 0, and then 1, 1, 1, 1. So for B BQ, do the same thing. You're gonna do 2 first and then do the last one from the order from left to right. Okay, that's the idea. All right, so now let's get into FSA. So FSA is a finite state automaton denoted by M. It contains 5 items, S, I, F, S0, and F. So remember, those are the notation that we're going to use for FSA, SMA. I mean, FSA, right? Finite state automaton. All right. So it will always have 5, S, I, F, S0, and F. So S contain the number of states, and then I will denote a finite input alphabet. Okay, so it would be like 1001, right? So that will be I. And then F will be the transition function. And then S0 will be the beginning of the initial state. And then F will be the final state, okay? Or the accepting state. So remember, it will have those 5. S, I, F, S0, and F, okay? It will tell you. All right, so we have 2 options. We can use a table or we can use a diagram. I want to show you both. So here is the FSA, M equal to SI, F, S0, and F, where S0, S equal to S0, S1, S2, S3. So this tells us that we should have 4 vertices, okay? And I equals 0 and 1, so I will contain the bits 0 and 1, and F will be S0 and S3. So that's tell us that the final state will be S0 and S3. We only have two final state in here, okay? So F will be the final or acceptance state. All right. So here's the table. Okay, so what does that tell us? So this tells us that at state 0, it will take 0 to S1, but then it will take 1 to S1, right? 0 to itself. And then at state S1, it will send 0 to S0, and it will send 1 to S2. And that's how we read it. And then S2, it will send 0 to S0, and then it's gonna send 1 to S0 too. So S2 send both 0 and 1 to S0. And S3 send 0 to S2, and then send 1 to S1. So that's how we present table. And from the table, we can obviously create a chart. In this case, we know that there will be 2 final state, which is S0 and S3. So we just use a double circle to make that circle for S0 and S3 because those are the final state that we have. All right, so here we go. All right, you can see here it's kind of mapped what we have. So we always start and then we add 0. So we have to double circle that because that's the final state. And you can see here 0 send 0 to itself. So that's why you see a loop here. 0 send S0 to itself. And then it send 1 to S1. So it will be send 1 to S1. And then S1 send 0 to S0, right? S1 send 0 to S0, and then send 1 to S2. So that's why we try to arrow there. And then S2 send 0 and 1, both 0 and 1 to S0. And S3 send 0 to S2, and then send 1 to S1. So that's how we use the table and create a graph based on it, okay? All right. Okay, so here is another example. So you can see here that they tell you the final state S0 or S4, or you can see the recognition like when they tell you this, okay, F, like S0 and S4. So that's the indication that the final state, okay? That's the notation of that. All right, so now we have 5 state, S0 to S4, and S0 send 0 to itself and S2. All right, and then S0 send 1 to S1, and then S1 send 0 to S3, and then S1 send S1 to S4. All right, and S2 send nothing to 0 to nowhere, and then send 1 to S4. Okay, and then S3 send 0 to S3, and that's it. S4 send 0 to S3, and also 1 to S3. Okay, so here is the graph of that. All right, so we see that we have two final state, which is S0 and S4, and you can see all the map. S0 send 0 to itself, and then S2, and then send 1 to S1, right? So that's another language that we have, right? So that's the idea. Okay, so from the graph, you can create a table. From the table, you can create a graph based on that. Okay, sounds good? Yeah. So now the language that recognitions by the FSA. All right, so suppose we have the string X. If it can be recognized or accepted by the machine, if it takes the initial state as of 0 to a final state. That's it. It doesn't care how many it's gonna travel through, but if it takes the initial state to a final state, then we said that yeah, it will be recognizing or accepted by the FSA. All right, so the function will be s of 0 and an x. We're gonna use the string of x to take the initial state to the final state. So we denote that L of M. So L of M is the set contain all string, all right, all the string that recognized by M. So meaning that it will take the initial state to the final state, then we can have the set M. So here is a few examples that you can see here. So when you see that we start, you take a look at the first example, we start right here, and then we go to S0, and you see that it's double circle, so it's the final state. So S of 0 take 1 to itself. So that's the only string that we have. Right? You wouldn't care here, that's a dead state, right? So it sends 0 away. So this one here go nowhere. So it's the non-final state. It's just a dead state that we send all the extra over. Okay. There we go. Okay. So the only final state is S0. So the string that take S0 to itself will be a 1, or you can do 1, 1. You can loop around that many times as you want. So L of M1 will be 1 to the n power, where n equal to 0, 1, 2, 3, 4, 5. Okay. So we talked about that, the clinic definition before, the clinic closure, yes. Now on the second picture, you can see here, we started, yes, we started. And then we go to S0, and then we go to S1, and we go to S2. So we only take the route 0, 1 to S2, or you can take the route 1 directly from S0 to S2. And then you can see that we send 0 away from S1 to the dead state S3. So that's how it's recognized the language. So it means the same thing like, okay, I'm gonna put 25 cents, or I can put 20 cents and then 5 cents, things like that. Okay. All right. So you can see here, either take 1 directly from S0 to S2 to finish the journey, or take a bit string 0 to S1 first and take a bit string of 1 to S2. So therefore, it recognizes two things. It recognizes 1 and the 0 and 1. So the idea M of M2 will be 1 and 0 and 1. Okay. And you might ask why we don't do it to the n power, because there's no looping, right? It's just one direction versus S0 in the previous example, you see S0 loop 1 back to itself, right? So we can define that. Now in the last one, you can see there are two final state here. S0 and S3. So S0 loop 0, and then it sends everything away. So that's one way to get the final state. Or you can go from 1, that takes you to S1, and then 0, that takes you to S3, and then S3 loop 0 and 1 to itself again. All right, so here is the set we can have. So you can see how you can take 0 many times as you want, and then that's your first final state, S of 0. And then you keep going with the bit string of 0, 1, 0. That will take you to S3, and then you are done right there. Okay. So that's one way to do it, right? So 0 to n, comma, 0 to n, and then 1, 0. Okay. All right, so that's how we look at the pictures, and we try to find the language that's recognized by FSA. Now, we can always go back and then construct a graph based on this. So here's the example. We want to construct an FSA that recognize the set of bit string that begin with 2, 0. Okay. Now, what does that mean is that it have to be 0, 0 right away, right? Because that begin with 2, 0. All right. So that's the idea. So yeah, so you can have star and then you go directly and then you're done. Okay. So S0, you have to go to S1, which take a 0, and then S1 to S3, S2, another 0, and done. That's the final state. Okay, so here you go, right? So you can start here, and then you go to S0, send 0 to S1, and send 0 to S2, and that will be your final state. And then you can loop the 0 and 1. So, you know, the 1 and from 0, and then the 1 from S1, we don't need it because, you know, the final state only needs to take 2, 2, 0, which begin with 0 and 0. So we throw that away in the set S3, so that it doesn't come back. So it's a wasteland on that, you can imagine on that concept. Okay. So another example is that construct an FSA that's recognize the set of bit string that contain 2 consecutive zeros. So now don't get misunderstood between this example and the previous one. The previous one enforced us that we must begin with 2 zeros. So the first 2 bit string have to be 0, 0. And then you have your final state. Well, this one here, you know, the first string doesn't have to be 0, it could be a 1, but as long as you have 2 consecutive zeros, it could be the 4, 0 and the 5th 0, they are consecutive 0, and then you can have that. All right. So in this case, we might want to define a non-final state where you can send every extra to that state. That's be nice. Okay. So here is the string, right? So again, we start it, and then we go to S of 0, and if you get a 0, then you go to S1, and then you get a 0, you go to S2, and you're done. All right, so we have 2 consecutive integer. Well, what happens if you hit the 1, then you keep looping again until you hit the 0. So you can see here that, okay, we kind of think of all the possibilities. There is a possibility that, okay, I'm gonna go here, and then go there. This is 2 consecutive 0. But then, you know, you can go from S0 to S1, but then you want to go back to that. You hit the 1. Then you're going to go back to that again until you hit another 0. So you have to get 2 consecutive integer, 2 consecutive 0 in order to go to the final state, versus the previous one is that, yeah, it's beginning with 2 0. So we know it is beginning with 2 0. So we have no option that we only take the 0. But this one here, you can take 0, 1, and then 0, 0. So that's just your journey, because, you know, as long as we have 2 consecutive 0, then you should be good to go. All right. And here we have, you know, direct deterministic FSA and non-deterministic FSA. So what we learned so far is the FSA. Okay, so and then the non-deterministic FSA is the one that have several possible next state for a pair of input and state. Okay, I mean that you can send 2 0 to 1 0 to S2 and then 1 0 to S3. It doesn't have a fixed amount of that we have. Okay, there's be more possibility. If you look at FSA, then it just sends 0 or 1. So you can send 0 to S1 and then 1 to S2. That's it. But for non-deterministic, I can send 0 to S1, I send 0 to S2, and then I send to 0 to S3, and then I decide to send 1 to S4, right? So that's non-deterministic FSA. And yeah, still contain the same thing. The set S with how many vector or how many circle we need, and then I will be the bit string 0 and 1, and then F will be the function that's going to transfer. As a 0 will be initial state, and capital F will be the final state that we have. Okay, you can see here that this is a non-deterministic FSA. So you can see that S0 send 0 both to S0 and S1. And then S1 send 1 both to S1 and S3. And then S3 here you can see send 0 to 0, S of 0, S of 1, and S of 2. So this is what we call non-deterministic FSA. The other one was deterministic FSA, where you only have one direction, right? You either have send a 0 to S1, then you cannot send 0 to any other set beside S1 because you decide that, okay? So you can see here the map. It's quite crazy because that's what it is. But again, anytime you have a table, you can always use that table and convert that into a map of the graph itself. Just follow the FSA, that should be good. Okay, and that's the last section of the semester. Thank you for your patience and your time for the whole semester. And this is the end.